Hello everybody, this is the video clip for chapter 5 and we still in 5.2, and this part it is about some applications of the continuous function. Okay, so let's look at this definition. If your f, okay, it is sending from the domain A to the real number R, it will say to be bounded if its range is bounded, which is there will be some positive real number m such that the absolute value of f less than or equals to m for all x in the domain. Okay, so this one, if we want to say that your f is not bounded, okay, on a on a, okay, we can say that for all m, okay, instead of there exists an m which is a positive real number, we can find, okay, because instead of for all x, we can find the point x depends on that m in the domain A, such that your f at this particular point, it is greater than that positive number m. Okay, for example, if you talk about f of x equals to 1 over x, okay, and your a, the domain, it is in 0 to infinity, okay, we can, I mean, of course, you know that your f of x, it is unbounded, right? Okay, as your x go close to 0, then your f of x getting larger and larger. How to say that, okay, or how to confirm that? We are going to let your m be a positive number here, and we are going to find, so we choose one of the point inside this domain, okay, and we know that because it is 1 over, so we use the point as 1 over m plus 1. Okay, why is that? Because as we take 1 over the large number, then it will be pretty small, and we know that the as your x getting smaller and smaller, your f of x getting larger and larger, right? And this one, your f of xm, this point, it is actually 1 over m plus 1, which is m plus 1, and it is of course strictly greater than m. So we have that your f of x, which is 1 over x, it is not bounded in this domain. Okay, however, if your f, okay, is continuous on the interval AB, okay, so it means that it is continuous with a continuous function, okay, with domain as the closed interval AB, then it will always bounded, okay, on this closed interval AB as well. Okay, this one, to prove it, okay, we are going to prove it by contradiction. Okay, and you need to try to think of something that you have learned before. For example, if you got a bounded sequence, then you can always find the subsequence, okay, that is converge. And if your sequence converge in a closed uh, and bounded interval, then, or in a closed interval, then that limit of your sequence will be an element in that interval as well. Okay, so that kind of thing that you need to think of. Okay, so let us first try to prove this one, as we told you that we are going to do it by contradiction. So let's say that your f, okay, is continuous on AB, but it is not bounded on this domain AB. Okay, so what does this mean? It means that again you can for any m, okay, for any positive value m, you can find the point x in the domain, pairing it with that m, okay, so that your f at that point will be greater than that particular number m. Okay, this is the technique again. When we have this kind of for all, then we can think of your m as each and every positive integer. Okay, so let's say that if your m is 1, okay, if your m is 1, then we can find your x1 in the domain such that your f of x1 will be greater than 1. If your m is 2, there will be your x2 in the domain so that your f of x2 will be greater than 2. Okay, it will be greater and greater as we change m. So for m is any natural number n, there will be the x sub n in this domain such that your f of xn will be greater than n. Okay, so this is how we construct the sequence xn inside this closed and bounded interval. Okay, so since this one is bounded, okay, then your sequence xn is also bounded by the Bolzano-Weierstrass, okay, theorem that exists a subsequence, okay, a subsequence, this is pretty important, xnk, okay, of xn such that your subsequence converge to some particular number x. Okay, but again this one is not only bounded, but this closed interval is also closed, so it means that your limit, okay, of your subsequence will be one of the element in this set. Okay, and of course, I mean, it's not only close, but your, let me just write down that your subsequence is also an element, okay, in this interval. Then your x, okay, the limit will be one of the point in this interval AB. Okay, and we just saying that your f is continuous on AB, right? So it means that your f is also continuous at this limit at this point of limit of your sequence x here. Okay, so what does this mean? It means that we have a sequence converge to the point x, and this point your f is continuous by a sequential definition, the sequential criteria of the continuity. Then it means that your f of x and k, okay, will converge to your f of x. Okay, all right, so because this sequence converge, okay, we know that the convergent sequence is bounded, so it means that your sequence here, okay, in terms of a function value f is bounded is a bounded sequence. Okay. However, can it be bounded? Can it be bounded? This one is a contradiction since, why is a contradiction? Since your f at x and k, okay, this one will always greater than, by the construction you see, f of any xn, okay, will be this one, sorry, will be greater than n sub k, okay, and this n sub k, it is actually greater than or equals to this k, okay, this one is by the definition of the subsequence, right, that we are going to take n sub 1, n sub 2, n sub 3, and the subscript will always greater than or equals to the real domain of the original sequence, right? Remember, and your k, this one, it is in n, okay. So what does this mean? It means that your sequence is actually not bounded, okay. So this one is contradict with the thing that we construct here, okay. So it means that what we assume, okay, what is it that we assume? We assume that your f is not bounded on the closed interval AB, okay, is not valid. So the conclusion is that your f is actually bounded on the closed interval AB, okay. So this is the proof of this theorem using the subsequence, okay. So another important application is that if your f is a continuous function on the closed interval AB, then it will has the absolute maximum and the absolute minimum on that closed interval AB, okay. So what is the absolute maximum? Your f is said to have an absolute maximum on the domain A if there is a point A star, and this one is very important, that your A star must be in A, such that your f of x, it is larger than or equals to f of A star, it is larger than or equals to f of x for all x in the domain. And on the contrary, if you said that f have an absolute minimum on A, okay, if your A substar, okay, it is again in this domain A, and your f of A substar less than or equals to f of x for each and every x in the domain, okay. So how are we going to prove that? Let us say that this interval is the interval I, okay, and we are consider the range, right, the range of the function f in this closed interval, which is your f of I, okay, which is the set of all value f of x, where your x is in the domain, okay, from the closed interval from A to B, okay. This one, of course, it is not an empty set, okay, because your domain is this closed interval A and B, right, okay. So by the previous theorem 5.2.9, your f of I is actually a bounded subset, okay, a bounded subset of a real number R, right, okay. So of course, if we talking about the maximum, then it is like the one that is close to a maximum is the supremum of the subset of real number, right, as you learned before. So let us talking about the supremum of your fi, okay, and we call it as s star, and the s sub star, it is the infimum of your f of I, okay. What we need to prove, okay, let us claim here that we are going to prove that there is a point, okay, because we really need the point here, okay, a star and a substar in this interval, close interval a and b, such that your f at a star, it is the supremum s star, and your f at a substar, it is your infimum s substar. Okay, so this is our assertion. Okay. Do you still remember what's the technique on the supremum? Okay. So for the supremum, if we draw a picture, let's say that this one is your f of I, okay. So the supremum is somewhere here, right, the one on top, okay. So if you subtract our supremum by some positive number, okay, usually we call it epsilon, then we know that there'll be some other element in the fi, okay, that in between s star and s star minus epsilon, right? So let us start from the supremum. Since this one is the supremum of your fi, then instead of using the epsilon, okay, we are using the integer, the positive integer n, okay. So for epsilon equals to 1, then it means that s star minus 1 over 1 is not an upper bound, okay, of fi. All right, okay. So what does this mean? If it is not an upper bound, okay, it means that there'll be the x1 in that interval ab, such that your s star minus 1 over 1, it is less than f of x1, and it is less than, of course, the supremum, right? So if your epsilon equals to 2, then your s star minus 1 over 2, it is again not an upper bound of your fi. So it means that there will be your x2 such that your x star minus 1 over 2, okay, will be less than x2, and then this one, of course, less than the supremum. Okay, so as we continue this process, okay, if you talk about epsilon as the positive integer n, okay, then your s star minus 1 over n, of course, is not the upper bound of your fi. So we can find x sub n in that interval, so that your s star minus 1 over n is less than f of x sub n, and it also less than your supremum, okay, for n is in the positive integer. So can you see this kind of trick again? Okay, so there'll be this kind of two trick. One of them is that we using it as a small number. Another one, previously we use it as a huge number. So it depends on what we are going to prove, right? Okay, so right now we have the sequence, right? We have the sequence xn, okay, here, which is in the interval a to b. Okay, so again, since this interval is bounded, then it means that this sequence is also bounded. What kind of thing that come to play with you again? So this Bolzano and Weierstrass, okay, will come to play with you again. There'll be the subsequence, okay, x and k, all right, that is converges, okay, to a number x star, okay, that should be the one that we're looking for. Okay, let's call it a star, sorry, to a star. Okay, the one that we're looking for here, okay, the a star. Why is that? Because you see that we already like kind of squeeze, right, squeeze your f of xn between these two number. Okay, so again, since your x of nk, it is in this interval, which is a and b, and this one is the closed interval, then your a star has to be in this interval ab. So this one is already a good candidate because we need it to be inside this interval. Okay, and because this one is in this interval and your f is continuous on the closed interval, so your f is continuous at this particular point. Okay, so it means that by the sequential definition of continuity, your f of x and k converge to f of a star, right? And by the construction, you know that s star minus 1 over n, it is f of xn, it is less than s star. In particular, if you're talking about the subsequence, it's also the same. Okay, so by the squeeze theorem of the sequence, okay, we have that your limit, okay, the limit as your k goes to infinity of f of x and k will goes to s star, okay, which is the supremum of your fi. But this one, okay, from this continuity, this limit goes to f of a star. Okay, so we have f of a star where your a in this interval, it is equals to s star, which is a supremum. Okay, so it means that your your a star, okay, is the point where your absolute maximum occur. Absolute maximum point of this function f in this interval I. Okay, so of course this one is only half of it, right? Because we just proved about the supremum or the maximum. Okay, what we need to do is to talk about the minimum, the absolute minimum. So this one will let you to do it by yourself at home, okay, as an exercise. All right, Okay, so for this video clip we go over the two theorem, okay, that is important application of the continuous function. The first one is saying that if it is continuous, okay, on the closed interval, then your range of the function is bounded, okay. And the other one is saying that if it is continuous in the closed interval, you can always find the maximum, the absolute maximum and the absolute minimum inside that interval, okay. And you already have been used this kind of theorem in your math 1 several times, okay. For example, if you talk about this a and b, and then you are trying to find the maximum and the minimum of this function, okay, which is continuous in this closed interval, then you can see from the picture, right, that here is your absolute minimum, and there may be your absolute maximum, okay. So if you remember that if you are given your f of x inside the closed interval a b, and in math 1, if you need to find the global or the absolute max or mean, okay, you just find your f prime x equals to 0 and solve for a critical value, and then you need to just compare, right, compare your f at the critical value and your f at the end point, remember, okay. And this one of course is a continuous function, okay. So this is what we already did in math 1, but we just prove it here, okay. So we'll see you on the next video clip with a more interesting kind of application of the continuous function, okay. We'll see you then. Bye bye.